Good day and welcome back for the fifth and final part of our discussion on optimization problems. As I indicated at the end of the previous video, you can find a class worksheet for optimization problems located in Canvas. Hopefully you have located that worksheet and you've spent some time working through these problems. In this video, I would like to focus in on problem number 5, which is a problem students typically struggle with. We have the following. A right circular cylinder is inscribed in a sphere of radius r. Find the largest possible volume of such a cylinder. i.e., can we maximize the volume of a cylinder that's put inside of a sphere? So let's go ahead and draw a picture. So I have the following picture. We have a sphere, and inside that sphere we have inscribed a cylinder. And the fact that it's inscribed means that kind of this top circular part of the cylinder and the bottom circle on the cylinder, those are sitting on the sphere. And what we know about the sphere is that it has radius r. So somehow what we want to do is write down a formula that represents the volume of this cylinder, and then we want to maximize it. So what we are going to need to do is introduce some notation and really try to exploit the fact that the sphere has a radius of r. So if we're sitting at the center of the sphere, we can draw a line down to where it hits the bottom of the cylinder. And if we call that distance y, the height of the cylinder then would be 2 times y. And in order to write down a nice convenient formula for the volume of this cylinder, we need to indicate its radius, which I will simply call x. So the volume of this cylinder would be pi times that radius x squared multiplied by its height. And the height is going to be 2 times y. And note once again, this is a common formula. Pi times x squared would be the area of the base of the cylinder, and 2 times y corresponds to its height. And in order for us to use calculus to maximize this volume, what we need to do is write it in terms of a single variable, either x or y. And that key fact that we have yet to use is that the radius of this sphere is r. And in our picture, if we add in that radius of r in the right spot, we have a right triangle. So we now very clearly have this relationship. The Pythagorean theorem tells us x squared plus y squared is equal to r squared. And just to briefly reiterate, it all comes down to kind of how we label our quantities and draw our picture to get that right triangle to fall out for us. So in terms of the equation above, x squared is something we can easily solve for. That is, x squared is simply r squared minus y squared. So the volume of this cylinder as a function of y is pi multiplied by r squared minus y squared times 2y. And if we go ahead and simplify this down just a bit, we would have 2 pi r squared y minus 2 pi y cubed. And we want to maximize this on what interval? And the thing for us to note is if you look at our y value in our picture, the smallest it could be just in a physical sense, whether it makes sense or not, would be 0. And the largest it could be, once again, even if it might seem a bit contrived, is if y is equal to the radius. And we now have a calculus problem that we can work with. So let's solve it. So v prime of y, just differentiating term by term, is 2 pi r squared minus 6 pi y squared. And what we would like to do is determine, are there any critical points between 0 and r? So we set it equal to 0 and we solve. But remember, the r that we see is a fixed quantity representing the radius. It's just a number. So we would have 2 pi r squared is 6 pi y squared. Divide both sides by pi. Divide both sides by 6, and we would have r squared over 3 is y squared. So that y is equal to plus or minus the square root of r squared over 3. And if we make a number line to the side here, we're looking at what happenings between 0 and r, and we have one critical point of interest to worry about in our interval. That would be r over the square root of 3, and we're thinking about the sign of v prime. Now, note, if you substitute in 0 or r, and you get back plus or minus, then we'll know exactly what happens in this interval. And when we let y be equal to 0, we get back a positive quantity. And when you let y equal r, you get back a negative quantity. So v prime is changing sign from positive to negative at this critical point. So your function starts off at 0 and increases and then decreases. So that critical point must correspond to an absolute maximum. So by the first derivative test for absolute max and mins, always justifying with this specific test that we are using. We are now ready to conclude on the largest possible volume. So it's not necessarily what value of y is going to maximize, it's what is that maximum volume. So by the first derivative test for absolute maximums and minimums, the largest possible volume is, and we can go back to our original equation way up at the top here for the volume and just substitute in this quantity for y. So we would have pi times r squared minus y squared, where y squared is simply r squared over 3, multiplied by 2 times y, which is r over the square root of 3. And note, you could simplify this significantly in terms of the r squared minus r squared over 3 and then multiplying it by this quantity, but I'm going to go ahead and leave it in that specific form. And I'm going to note, units were not specified in this problem, but since it is a volume, I'm going to go ahead and just write units cubed, but if you left that portion off, that would certainly be fine as well. When units are included in the problem, that's when they absolutely must be included as part of your answer. And that completes this current example. And let me remind you, you can find full solutions to the worksheet located on Canvas, and there are many good suggested problems from the textbook as well. These are problems that students usually find challenging, which means that you really do need to schedule out or set aside that time to work through these problems, but you're not alone. When you have questions, do not hesitate to reach out or drop me an email. So stay tuned and take care.